Now, what happened? In essence, you started with a dimension. Okay, a dimension space. Okay, ended up with how many dimensions? 2 to 3 dimensions. Okay, right? What's the first dimension? First dimension is along the first principle. Okay. So what have you done? So essentially, you go from A to 3. Okay, you go from A to 3. And I've just given you a case where not only have you given reduced from A to 3, the first one is so important. The second one is a lot less important. The third one is a lot less important. And the fifth one, blah, 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 is much less important. Okay. So dimensionality reduction, okay, I capture the essence of K dimension space. Okay. Into data distributed in K dimensional, where K is much less than K. Now notice, there's no order in here, right? With principal component, I'm going to say the first one is more important than the second and more important than the third. In this case, I'm just going to say reduce down to K equal to 3, all equally important. Okay. So there's no internal order like principal component. So this is more general concept. Yeah. Okay. So that's it. Just K down to K. E.g. So PCA is a form of dimensionality reduction. 8, 3. But dimensionality reduction does really mean PCA, right? Right. So PCA is more special because it does that special. Now, in your data, it depends on what your project is. Okay, I would say that if your project, and this is from prior knowledge, if your project is analyzing financial movement, chances are financial movement, they have relationship between each other. Definitely yield curve, all the yields, all these guys have relationship. So definitely, I wouldn't just do dimensionality reduction. I would actually do PCA. But in other things, it would just be general dimensional reduction. Okay. Now, dimensional reduction doesn't really have a DADR. You know, I just use a full word. Doesn't mean. Doesn't always mean. Okay. Doesn't mean. Okay. Doesn't mean. By itself doesn't mean. Okay. Note, this is very important. Okay. And the difference, you know, obviously this is going to be one of those things I can ask you. Okay, fine. So the essence of dimensionality reduction is to reduce high dimension into lower dimension. Okay, that's it. Okay, high dimensionality reduction. That's it. Just reduce high dimensionality into low dimensionality things. Okay, so okay. Let me give you the name. Let me give you the name. The two most ubiquitous dimensional reduction algorithm as of 2021, just to be sure, are these guys. Okay, 1 and 2. Okay, 1 and 2. Now, I would explain how. Let's explain autoencoder first. Okay, autoencoder first. Now, if you think about it, okay, let's look at multi-layer perceptron. Let's find a picture from the internet. Okay. And let's look at this guy. Okay. Just ignore everything here and just look at this. Okay. You guys remember last time when we have multi-layer perceptron, right? So okay. We call LP, right? Layers of perceptron with usually with just one output, right? So output would be like cats and dogs or something like that. Well, now imagine that output same dimension as input. Okay, so if I put in a vector of 8 dimension, I want to recover 8 dimension. Okay, and then in the hidden layer, okay, you have fewer neurons than dimension of output. Yeah. So let's look at the picture, right? So if I look at multi-layer perceptron, the picture tends to look like this, right? So you have something like that. Input 1, 2, 3, 4, 5, 6, right? That's 6 dimension, right? 6 dimension, x1, x2, x3, x4, x5, x6. It goes to some middle layer. Now the middle layer can have more than the input, like this one, right? 4 to 5. But anyway, the point is you end up with just one output, right? Because that's the job you wanted to do, some kind of function. Okay. Now, so you start with 4, you can go up to 5, you can go more layers, It doesn't matter. The point is you go from original vector dimension to just 1. Now imagine, I don't want to go down to 1. I want to go down and then go back up to original dimension. So that's what this picture comes down to. Okay. So it could be input layer, go to this layer, go to output, or it could go to successively smaller, right? Smaller and bigger, right? So it can go in one shot, or go to 1, 2, 3 step. Okay. Now, what happens is here. This is the interesting. This part and this part are two very symmetric. So you can notice that the output has the same number of vector or value as input. This one has 1, 2, 3, 4, 8 neuron. This one also has 8 neuron. This one has 6. This one, so it's mirror image. It's mirror image. But the key important is down here, the dimension is less. So what this does is it goes from 3, 8, 1, 2, 3, 4, 5, 6, 7, 10, down to 3, back up to 10. Okay, so this goes down to 3 and goes up to 10. So this part is the encoder part. This part is the decoder part. Imagine that you get charged by the number of dimensions. You get charged by the number of dimensions. If you can store the data in 10 dimensions, it costs a lot of money. It costs a lot of money. If somehow you have a neural network that can do this, and then the output reproduce, okay? Remember, MLP, you're trying to decide if the picture is a cat or a dog or whatever. Good credit, bad credit, good person, bad person, cancer, not cancer. No, this kind, the output is supposed to look like the input. So it's trying to recover exactly. So that's why it's called encoder, decoder. You want the output to be exactly the same as input, except before it gets to the output, it has to squeeze down to lower dimension. If you can do this successfully, what it means is that the original movement in 10 dimensions can be described in just 3 dimensions. This would be like principal component. Okay, so analogy to our problem earlier would be, this would be the 8 yield, and there will be principal component number 1, number 2, and number 3. That would be an analogy, except the principal component has that order. The first principal component has all the movement, and whatever is left, the second principal component. In this case, these are equally important. The point is you go from 10 down to 3 and successfully recover. So think of autoencoder as data compression. Okay, you have big data set, you compress into smaller data set, you put in a thumb drive, and then you recover. So this is like a compression, decompression in data, in picture, in storage, right? You have picture, many pixels, you compress the data, then you decompress. Now, obviously, if you decompress, there'll be some loss most of the time, okay? So this is what's called lossy compression, not lossless. So the input picture can be a cat. You can reduce it down to smaller dimension. You recover picture of the cat, but maybe it's a little bit noisy. It's a bit crazy. So it's not perfect recovery. Okay, it's not perfect recovery. It is some kind of a lossy recovery. Okay, so if you can do this, and then you just throw this thing away, this neural network here perform dimensionality reduction. Okay, because it has all the information contained in the original, whatever, 10-dimensional space embedded in 3-dimensional space. So this is how autoencoding works. Okay, so this would be this guy. So you train the neural network to reproduce input at output layer. The middle part is the dimensional representation. Okay, the middle part. So this picture here is the middle part. Now, it's not like principal component, so you can't say that this is more important than this one. No, it's just down to 3, equally important. Okay, all just as important. So that's so like think of analogy lossy it's not perfect. Usually it's not perfect. If you get it perfect, fine, but usually not. So I'm just gonna the important thing is this. That's lossy is not the essence. You don't want it to be lossy. Okay, data compression scheme. Yeah. Except the difference is now what would you do that for? What would you do that for? Why? Okay. Now in data compression, why would you do that? Because this one is big data, right? Huge. You want to put it in the size that you can put in a thumb drive, right? And then recover it. Okay. But assuming that that's not your problem, why would you want to do that? Well, one of the most obvious thing is you want this to be small enough that you can visualize. One, visualize. Okay. If you shrink two or three dimension, you can what? You can plot. Right? One is visualization. Okay. Two, you can think of it. This is what's called pre-processing. By reducing the variable count. Okay. Reduce a machine learning parameter. Okay. And possibly. So this is more like technical thing. This is what data scientists would definitely use it for. Okay. But first of all, before you do anything, it helps you visualize your data. Okay. So if you think about it, okay, if you think about it, now I haven't, so the other thing is called TSNE. That's another popular one. I'm just going to give you the video so you can watch it. Okay. This is also very, very useful, but no. In pre-processing, okay, this is very important, but let's focus on this. In visualization, if you think about it, okay. Now I'm going to say visualization or representation. Okay. So let's talk about, let's talk. Okay. I'll give you 3 countries. Thailand, Laos, Peru, India, China, UK, US. Okay. If I can represent socio-economic data of each country. Okay. And social representation status of each country with say 1,000 variable. Okay, what can I do? I can say whether Thailand is closer to Peru than Thailand is to say India. Can I say that? Okay, based on 100,000 parameter, right? Based on 1,000 variable. Okay, now if I can also reduce dimensionality, reduce the 100-dimensional vector into 2-dimensional vector, I can also list plot individual country, right? Right? And that's where the picture, this one, okay? If you go to this one, I think I gave it already. You should have downloaded it already. Have you downloaded the COVID paper? Not your head if you have, okay? So I'm gonna assume, so this is this picture, okay? This one, right? So that's the PDF, okay? So if you go down here, right, this is exactly what gets done, right? There, okay? Oops. Originally, the data has all kinds of dimension, right? But based on this data has to do with COVID death rate, vaccination, whatever, I don't know, population density, okay? If you reduce all the dimension into 2D, you can plot different countries. Now, this country, all of these countries have vectors of 8, 10, 20 dimensions. But it computes down to see, so what it says is that with respect to COVID data, Peru and Singapore are closer together than Peru is to Vatican and New Caledonia, for example, okay? So these are all different countries, okay? So you can compare how close they are in the original dimension, no problem, no problem. You can't visualize it, okay? In this case, you can literally see, different groups of countries. This is like Japan and Singapore are close together, and Monaco, and and as a continent also has its own statistics. This is another block that are similar. Papua New Guinea are very similar to Afghanistan and Marshall Island and Kiribati. Whereas Bermuda, Cayman Island are close together. Brazil and Panama are very similar, and so forth, right? So this is viewing dimensionality reduced. So that's the paper, okay? So that's basically what's done here, okay? Okay. So you can list plot in artificial dimension, okay? So this is very important. And you know how else is it important? It's also showing how you have different cluster data set. Okay. Now, how is this done in Mathematica? Obviously, it's a lot easier to do things in Mathematica. All right, you could just call some kind of top-level function. Now, I want to point out to two different functions in Mathematica. This is the style of Mathematica. One function just performs what you ask it to do. Okay, so you reduce 8-dimension points in 8-dimension into points of 3-dimension. That's called dimension reduce. Okay, or you can create a function like this. Create a function that does this job, and you can save this function to apply to another data set. Okay, so essentially, if you want to do it once, you just ask it to do it. Reduce 8-dimension to 2. I think the default is to 2. You can specify what you reduce it to, but by default, I think it's 2 because that's the most usual case. So when you use this dimension reduce, go to Mathematica, bits and pieces, bits and pieces, dimension reduce. Okay, go to F1. Okay, so that gives you, whatever data. So in this case, okay, you have 1 point, 2 point, 3 point, 4 points in 3-dimension. It reduces to 2-dimension. You still have 4 points, right? So with the yield curve, right? With the yield curve, you can do what? 1 point, 2 point, 3 point, 3, 4 points, right? So instead of having 8, you have 2, okay? But it would not be the same kind of thing as principal component. So this is what dimension reduce does. You use it once and you're done, okay? If you specify 1, then that reduces it to 1 dimension. Okay? But if you use dimension reduction, okay, and you supply it with the data, it's going to give you a function that you can call later. So this becomes a function. Okay, so let's look at some example. Okay. Application, data set visualization, so forth. Okay, well, this is easy. And so this is doing it, setting the function and doing it many times. Example, basic example. Okay. This is your principal component. I think there's some very interesting picture. Hold on, let me look at. I saw some example that were use case. So anyway, so with principal component, I have to compute the principal component, then project the data. But with this, it just gets you the projection into 3-dimension. So this is going straight from 11, whatever 10-dimension down to 3. So this is basically how you would use it. Okay, so by the way, these are 2 things. Okay, so this is asking Mathematica to do something once. This is creating a function that does it. Okay. Now, think of what happened here. Think of what happened here. Did I close the picture already? Hold on, let's go back to that paper again. Let's go back to that paper. Okay, this is, I want to go to the compression, right? Okay. By the way, I think this is to plot in original variable. You have to choose which pair, right? You can move it 2 at a time. But once you do the compression, okay, now, here's the deal. Okay, here's the deal. Here, what happened is I have, what's the original dimension? I don't know. say original dimension is 20. Okay, I don't know what it is. Okay, original dimension. Okay, so you have here, okay, in dimensionality reduction, start with K numerical, okay, variables, end up with K, also numerical, whereas K is much less than K. Okay. But you have a principle, not principal, component. The way you did it ensures that points that are close together in K dimension remain close in K dimension. Yeah. Likewise, points that are far apart this is the most important concept. Okay, it doesn't matter what algorithm it is. It could be TSME, it could be autoencoder. Okay, this is the feature of dimensionality reduction. Okay, points that are close together in K dimension remains close together in K dimension. Okay, but these are numbers. These are numbers. Okay, so somebody very smart, what if you can apply this principle to, say, word? Okay. In other words, come up with some kind of algorithm that ensures okay. Now I'm going to change, I'm going to paraphrase. I'm going to say that words that are close together in most contexts. You know what the word context, right? Context means like, you know, if you see word like cartoon and manga and, you know, all kinds of stuff together, be close together. Whereas you see words like Rembrandt and I don't know, so the representative painting of the Dutch master or not Van Gogh, it's later. You see Rembrandt, you see the classical painters together, basically, right? The Dutch painters are all together, and the modernists, Picasso and Van Gogh, and would be together, or Mondrian would be close to Kandinsky, you know, names that would appear together, right? You can think of people as appearing together. So pop star, right? So whatever, your pop star, your K group, your K band group, they would appear together. You would probably not see any kind of internet or blog that mentions K-pop close to Beethoven or you know, Bach or Stravinsky and some K-pop band. You probably don't see that together, right? So you see Brahms, you see Mahler, you see these people together, okay? So Sibelius, all these guys are kind of like together. Whereas the K-pop, I don't know, the K-pop people, they would sort of like appear together. So words or names or things that are close together, that instead of saying close together, that tend to appear within common context. Okay. Now, get represented by numerical vectors that are close together. And then words that tend to never appear within common context would then get represented by numerical vectors that are far. Now, in this case, are you reducing the dimension? Well, you can think of word as a very high dimension thing. So when you go to number, it's a lower dimension. Except when you get to numerical vector, usually you don't get to 2 or 3D dimension. Okay, you don't get to 2 dimension. You can get to something like, say, 300 dimension. 300 dimensional. Okay? So your focus here is not to reduce, but your focus here is to keep that principle, This is called word embedding. And why is it good? Why is it good? Because you can do something clever like this, okay? Let's say you have, and this is a classic example, by the way, okay? King gets represented by X, which is 300 dimensional vector, numerical vector. Okay. Man, male, get represented by X1 and X2. Female, X3. Okay. And then, okay, and then you do this. Okay, you calculate X1 minus X2 plus X3 is equal to X4. Okay. Now, can you do that? Can you do that? Yes, you can, right? Because you are talking about vector subtraction and addition, right? Can you do this? Can you do king minus male plus female? You can't, because it's a concept. Okay? So, no, you cannot do concept algebra like this. But you can do vector addition, right? Well, like X1, okay? you can easily the magic is that X4 will be close, very, very close to the representation of Queen. Okay. And this is something sometimes called word algebra. So this concept giving rise to the concept word algebra. Okay, or concept algebra. Okay. Okay. In other words, you add x3 to the difference between x1 and x2, and you get this. And then you go to your database and see which word gets represented by the number that's closest to x4. Okay, so Queen's representation would be something like x5. You find out that x4 is closer to x5 than any other word. Okay, so this is the most fundamental step of NLP, natural language processing. Okay. So what you learned today, yeah, even though I was talking about, dimensionality reduction, just so that you can look at countries that are close together. Now it's not countries that are close together numerically, we talk about concept. Okay, so now you can imagine that, let's say I call this NLP, okay, word embedding of, say, brands close to word embedding of, say, this. Far from word. What's a Korean pop thing? Give me a band. Say Blackpink, right? How do you say Blackpink? Black. Big P or not? Presumably, or is it one word? Well, whatever. I don't know. I don't care. Okay, right? Something like that, right? Okay, or you can do something like word embedding of Brahms. Sibelius is good. Minus word embedding of, say, violin. Let's just say Wieniawski. Minus violin plus word embedding of piano. Okay, will be close to word embedding of, say, Liszt. Spell his name right? Okay, I just misspelled Liszt. Then Wieniawski, let's make sure I don't butcher nice people's name. Wieniawski. Okay, why? Because Wieniawski produces violin concerto, very technically demanding. for violin. But I take away the violin, I add piano, and you get people like Franz Liszt or Chopin or something like that. Also very technical, same period, same style, very virtuoso, but piano, not violin, something like that. Okay, this is called word embedding. Okay, now, right, I would suggest that you go to this paper, but instead of going to the paper, oops, where's that paper? Okay, also go to the code. It talks about data set. You know, I have my son with the data set data structure because he didn't know about data set structure. So working with data set, you get a lot of examples from that. Okay, so this part 5 here, I'm not going to show. This part 6, right? Mathematical function you would likely need. Now, this one, I might come back to it later, but from looking at your project proposal, you guys are doing pretty well. But basically, all I'm going to do is say something like input, output, data, sourcing, data, right? Okay, like a working data structure. This table data set. Now you can get data structure. You can have some kind of data calculation, building, now, and all this, you obviously have visualization everywhere. Let's do this. Okay. Okay. So we might come back to this, but I think you guys are doing pretty well. So I want to quickly go to project discussion. So where are we? So where are you guys? Right. So this is before we run out of time. Document. I just replied. Okay. Okay. So let's go to our bits and pieces. Okay. Begin. Oh, good. So let's take this the first sheet. First sheet. 1, 2, 3, 4. 1, 2, 3, 4, 5. Let's take a 6. Start with Panit. Okay, good. Okay, so this is it, right? So how many we got? We got 44, right? So let's say sample equal random sample range 44, right? Okay. And let's take 10 of you guys. Okay, and 1, 2, 3, 4. Okay. let's take, let's make this repeatable. Oh, never mind. This is good. So let's take roster sample 4. Okay, here are the lucky ones. Okay, ครับธนกร ณภา พิชัด you have the floor. นั้นเดี๋ยวอาจจะไม่ต้องอัดตอนนี้ก็ได้น้องจะได้พูดสบายๆนะครับนะจ๊ะนะ โอเค raise your hand ธนกร you are up you have 2 minutes what happened okay okay so oops no. Okay okay ครับนัทภูเก็ต you're up hello okay we have to do this fairly quickly so okay Benedict
hello ครับ
where are you okay
yes
you have I'll give you a bit more time since you feel no sure so Benedict you go
so just explain what my project is about, right?
You feel free to share your thing
So
you can start with the homework you turn in
okay so
share your screen
I want to say at first I was thinking of getting data about alcohol consumption and finding out why people in certain countries consume more alcohol than others. Like, is there any external forces such as the economy and stuff like that? But I couldn't find like the right data, so I'm kind of pivoting my idea to, what does consuming a lot of alcohol does to the economy? Does like people have a higher suicide rate? Does people have less jobs and stuff like that? So I'm still kind of figuring out what my project will be about from the data that I found from alcohol consumption. But what I wrote in my latest work is that I found like a data of the rate of alcohol consumption by the liters and what the effects on like and also some data of like suicide rates and also data of jobs rate and stuff like that. So I'm trying to see what I can do with this data. I'm still kind of clueless at the moment on what I could do with it.
Okay. So you will take some form of, I guess, supervised learning because you do have a target in mind, right?
Yes.
Okay. So yeah. So you can also, you can also do what I show in the COVID data. If you follow through that, there'll be some that is supervised learning, some that's unsupervised learning, and then you can put country data and then take alcohol either as part of your variables, total variable that you do clustering on, or you can make it your target variable, right? Like
yes.
in the COVID thing, you see that the COVID case and death is also part of the whole data set. So you can do some sort of like clustering for the whole data set, or you can separate COVID cases or death as Y and use the rest as your X. Okay, so it's that kind of thing as well. So you can have country information that has to do with alcohol and not having to do with alcohol, and they do some kind of clustering or dimensionality reduction on that, or you can make alcohol a Y and then try to make a regression type thing. Now, let me just add this for you. Okay, check this out in the line group. Out might help here. Okay. Okay. So very good. So let me cut you off. Okay. Have you got anything to share with your friends?
Not at the moment because I just pivoted my idea in my recent assignment. And
okay.
Yeah.
Fine. Okay. So Benyapat Suvira Kanon.
Hello.
So Benyapat, where are you? Raise your hand. Oh, I see. Okay. ครับผม very good.
I've changed my project from analyzing trends in the fashion industry to analyzing and predicting the prices of pizza.
What again? Sorry. From fashion?
Yes, I changed it from fashion to prices of pizza.
Pizza price. Okay. Okay. What do you want to do with pizza price?
Pardon?
What do you want to do with pizza price?
I want to predict it from like different prices and based on their sizes, topping, their meters, and like their sauce.
Okay. Okay. Okay, that's interesting. Now, what kind of database are you going to be working with?
I found one data set that there's like 8 columns.
Can you type it in the line group?
Yes.
Got it? โอเคครับ
โอเคค่ะ
you have to I can't see you yet I can see your face I can't see your screen sorry
I send it through the line.
oh okay got it Kaggle competition price prediction very good price data set it has see what's so nice about Kaggle data set is all this all this sort of like preliminary analysis that you would have to do in fact I should teach you to do all this thing as sort of thing that you need to do doing basic histogram and the distribution and all that a lot of it is done for you so that's good okay most of the time even this page that we have all detail okay I can share now I have this okay so this thing here right all this and it has all this metadata about what kind of field it is it's numerical it is currency in this case currency or something like that and how many classification and all this okay this is something that you normally would have to do yourself but with Kaggle a lot of time they just do this for you okay good very good okayครับthat's very good so this is your pizza prediction data okay so now Benjapat Kanitha
Can I go next?
Kanitha
May I go next, please?
who
I have Pasit, the last one. I have to leave at 4. So
oh okay is that all right Kanitha your friend has something urgent to go to
Yes ค่ะ
okay
Can I please go after Pasit as well? I have an event to attend at 4:20.
okay Prasit
อาจารย์ครับ excuse me นะครับที่อาจารย์เรียกชื่อแต่ว่าผมเข้าห้องน้ำผมไม่ได้ยินครับผมขอ
okay Prasit ครับ go ahead
so my data is about an NBA player, list of NBA players, and I can show you like a similar stat.
okay go
Can 1 second. Where is it?
okay so ธนภูมิพิมนิพาจีนิชาคณิษฐา is prepared so you can data you want to share in the line group just key that in or the screen okay ครับ
I'll share the screen.
okay that's it go
So this is the stat I have. So there are stats in each categories, something like this. And so basically I want to create an algorithm that helps
so
me
these are
predict.
sort of like performance right these are performance
Right. Yeah, this is like performance. Yeah.
good.
So I want to create like an algorithm that detects which players is better. So I talked with TA. Initially, I wanted to like add salary and create like sort of like the more you play the player, the better the player are. But there isn't a stat that comes with salary, and I'm trying to find a stat that comes with the salary, but there's only like stats that only has salary and stats with only like the in-game stats. So I think currently I'll try to do it as like in-game stats. So some example might be like minutes per game and usage rate per game. So with that, so an example like Steven Adams play 55% of the game's minutes, and his usage rate is only 17. With that, we can assume that if we create a scatter plot, we can see that the lower the minutes is and the higher the usage rate is, we can assume that that player is more valuable to the team
Yeah,
and
sure. Why
play
not? You can use that as a proxy.
play more
Yeah, good.
roles, yeah, and play better as and like the one that controls the team, something like that.
Good.
So yeah,
good.
that's pretty much what I'm currently doing. But there's also like with this stats, there's also like a lot of like errors. So something like some players only took one shot the whole season and he made it, and that's like 100% rate of success, which
Yeah.
is quite inaccurate. Yeah, so I'll try to create an algorithm that eliminates that as well. So maybe like at least 4 shots a game counts, something like that. Yeah.
This
That's my
kind of, by
stats.
the way, what you just mentioned is a lot more important than you might realize. This important of creating what's called a baseline. What is the real baseline of certain aspect, right? So obviously you want people to have more shots and more success per shot, right? So if you
Right.
base your criteria based on percentage success, the guy who only took one shot and get 100%, that's going to be, look pretty good, one hit wonder kind of thing. So yeah, this kind of baseline, this kind of constructing the variable that makes sense, it gets very tricky. And it's one of those things where as a data scientist, you cannot decide on your own, okay? And this is my advice. Never decide on performance metrics on your own. Make sure that you do that in conjunction with your clients or the user of your program. Because you can make a good prediction and then again you pick up some guy who's like a one-hit wonder and that's useless. So anything that has to do with performance metrics, never decide that on your own. Okay, good. Okay, Kap. So who was the other guy who has to go? Very good job, guy. Next guy.
Can I leave Zoom now?
ภาษิตใช่ไหม Go ahead. Yeah.
ใช่ครับ โอเคครับสวัสดีครับอาจารย์
And who's the next guy? The one who has to go as well.
I have to go at 4:20 ครับ. Is it okay if I go?
You have to go at 4:30.
4:20 ครับ
4:20. Okay. Who are you?
ธนภูมิครับ
Thanapum. Okay. Go ahead. You have the screen.
Wait a second. Okay, so my project is going to be a license plate reader. So it will be a license plate reading system based on Python, and it will be able to read a license plate in real time and perform actions accordingly. Yeah, so what I'm planning is like first I will have a camera that will capture a live video feed, and then that will be sent into a computer which has the model on it. And then the computer can recognize the license plate, and then if it matches, let's say, a list of license plates that belong to like a certain car, for example, then it can perform. They can perform like actions based on it, like maybe send a message or like open the gate or something. So for the core libraries, I found like we can use OpenCV to help with.
OpenCV is very good for that. Yeah.
Yeah, and I found an existing like model that someone already developed for Thai license plates. So I'm planning to like maybe if it's possible, I would like to implement that, make it like kind of like more simple for me. And as for the testing data, I would like to like take a bunch of like pictures from like that specific camera angles, but under different conditions. So like different time of day, different weather conditions, and like different speed of the vehicle. So yeah, that's it.
Yeah, I think if I recall correctly, 4 or 5 years ago, was it? 4 or 5 years ago, I was taking a trip throughout UK, and I think I was stopping by I think University of Leeds on my way up to Nottinghamshire or something, and they used that basically. Well, it was a rental car, it was a rental car. I just drive up and it just takes a shot of the license plate, and for whatever amount of time that I was parked, it billed me for that, and so it's quite convenient. Yeah. So for English, it's already has been used for many years. For Thai language, The difference would be that the block letter. So I think this is actually a two-step process, by the way. The first step is to sort of localize the license plate and also localize the digit. Once you localize the digit into like a block subframe, then it goes to an optical character or character recognition. That's quite easy. So the difference between the Thai and the say UK license plate would be the placement of the alphanumeric field. Okay, so that's good. Okay, so I think UK license plate is very long. It's quite long. Thai plate has a it's a different framing, but it's quite easy to apply one from the other. So that's good. That's good. Yeah, OpenCV is very useful. In this case, yeah, I really I'm glad you're using Python and not building things from scratch because it's already implemented. I think you just pull the pull request from GitHub, right? Or it's already
yes,
before. Okay.
Yes.
Very good, Kap. Okay,
Okay,
go
thank
do
you,
your thing. Okay, Kap, see ya.
You.
Okay, let's go to Benyapat. You already did, right? Kanitha, ka? Kanitha Gunasin. Kanitha.
ค่ะ
Ka. Okay, raise your hand. Where are you? Can't see. Okay, I see you. You're in the dark. It's okay. I don't have to see your face, but you might want to share the screen.
Can I send it to line group
Okay, what you got?
แป๊บนึงนะคะhere's my data. So basically my project is like I create
You haven't grabbed the. I can't go in because you have to make it public. You have to make it public.
oh sorry can you access it? No.
Okay. Heart rate, emotion, alert. Heart
Yes.
rate, 95. Okay. And this is who are we talking about? Sad, alert, stress. Okay. So 1 day of data. This is from a wristband or something, yeah?
It's a sensor attached to dogs ค่ะ
Oh, okay.
ค่ะ
Well, I'm not surprised then. Dogs tend to be very alert, right? If you do this for a cat, it's probably going to be sleeping every. Okay. So what you want to do with this?
Basically I just want to compare the heart rate and interpret the data to like predict the emotion ค่ะ
This is this is going to have one problem because chances are whatever the data that this little health thingy, okay, records, it's going to have its own rule basically, right? And assuming that the dog color is no more advanced than human color, chances are it can only detect just the heart rate. Okay, so it can't, for example, detect things like skin moisture or, you know, this thing that I'm wearing detects my heart rate, and if I ask it to, it can also detect blood oxygen, but blood oxygen is expensive computationally, so it doesn't do it on a continuous basis. The only thing that it keeps on a continuous basis would be my heart rate and ambient temperature or whatever, okay? Chances are, if you do this, you won't get the right, what's the word? I think that the emotion cannot be predicted just from heart rate. I think what this thing does for your dog is also going to overlay other information like accelerometer. Like this one has accelerometer, right? Right? So if your dog collar measures heart rate, accelerometer, or orientation, or step count, that thing, and use all that to make prediction of emotion, but only gives you the heart rate information, right? That's like saying the algorithm takes 5 parameters, but only shows you 1. It's not likely that you are going to be able to build any kind of prediction model. You see what I mean? So
Yes.
I don't know what kind of device you have. Chances are maybe you have to pay for things like accelerometer data, because from looking at this, right, it only has time, heart rate, and alert. It's basically, I can tell you right now what's going to happen. The model is going to predict alert, because if you do the count, use a mathematical function count, alert accounts for over 95% of your data, I think. So chances are whatever model you put it to, it's just going to predict alert. Okay, so you have 2 problems here. One problem is alert overwhelms any other states. Second, and this is more important, okay, the fact that alerts overwhelm other states, you can perhaps correct for it, like oversample other states. The problem I think you have now is that the device only allows you to download heart rate. And it's probably not going to use, it's not just using the heart rate to predict emotion. It's probably going to use a whole bunch of other things, accelerometer probably. Okay, so unless you have that too, you can't reverse engineer the prediction. Okay, because actually you're not doing the prediction. The device is making the prediction based on heart rate, which it gives you, but based on something else that it's not giving you. So when you try to make a prediction model, what you're trying to do is reverse engineer the algorithm within that device. But because they want to sell you the device, if they give you all the variable, you are going to be able to reverse engineer the emotion prediction algorithm. So chances are this same company is not going to give you all the variables that you need to make the prediction. You see what I mean? So it's so in other words, you're trying to make a prediction from a prediction. So the company that makes prediction is probably not going to reveal all the variable that it uses to make the prediction. Otherwise, anybody, you, me, anybody can reverse engineer this algorithm, right? Using machine learning, and then create a new company that predicts dog emotion. Okay, so chances are you won't be able to do this project properly. Okay, again, because you essentially you're reversing engineering things that they're trying to hide. No, they're not gonna say, okay, we use these 5 variables to predict emotion, and everybody have access to it. Because after all, I think you have to pay for this device, right? It's a commercial device, right? So yeah, so I can guarantee you with all 100% certainty almost that it's not making emotion prediction from heart rate.
Excuse me, Professor. Actually, this heart rate actually is of my project, and I just bought the heart rate sensor and write the code in order to make it into emotion. So this is not others people data, but it's like I collect it manually. Does that make sense?
So you actually have at 9:47, 9:23.
I just test on one dog only.
Oh, okay. In which case, the problem you have will be the first problem. The fact that most of the time your dog is alert. And really, heart rate and stress and one variable can only get you so far. One variable can only get you so far. If you make this list plot, just take this, okay? Just make alert equal to some number and stress equal to some other number, right? and you make the scatter plot, you're gonna find that all the heart rate, virtually all the heart rate. I mean, I see that some of the heart rate is 0 and you still have alert, and the dog is obviously alive. So it has 0 heart rate and it's still alert. It's very unlikely that this data collection is going to allow you to do the project. So if you want to do something similar, try what your friend did. Maybe go to Kaggle, go to Mathematica repository, something about heart sensor data. Okay, you probably will be able to find something like this for humans. I'm not sure about dogs. Okay, so maybe something like emotional stress data for dogs. I don't think you will be able to create any meaningful prediction model from this. Okay, heart rate can only get you so far, really. Okay, and so maybe try, I don't know, try public data set. Just Google something like public data set dog emotion. I don't know. Dog emotion data set. There it is. There is Stanford dog data set in Kaggle. Okay, so maybe use this. Sorry, what's your name? Kanita?
การทิตาค่ะ
Huh?
การทิตาค่ะ
Kanita. Share out. Okay, or maybe something like this data set. Okay, or check out. I don't think you would be able to do that. You definitely have a problem if you. I know you love your dog and everything, but start with other people's dogs first.
ได้ค่ะ
This is also good. Stanford dogs. This is also good. Check out. Okay, check this guy out also. It's also very good. Okay, Naka. So you can do that. Make the training model, then apply to your dog as a testing. Okay, but you definitely can't build your model from your dog. That's almost impossible to do. Okay. Okay, Kap. So Nicha
อาจารย์ครับ อาจารย์ครับ can I go like next because I have something else that I really need to do like very soon.
You have to go as well. Who are you?
I'm Tanagon, the one who told to show up at first.
Okay. You go to the back of the queue. Nicha first.
อาจารย์ครับ I also like not took it that you call at the first. I didn't hear your first.
Okay. You come later. Nicha Rattanambon. Nicha, huh? No, this person. Nicha. Okay, we go to Jean.
Okay, hi. Me share my screen, please.
Yeah, go ahead.
อาจารย์โอเคครับได้แล้วครับ Okay, I think I shared my screen. Can you see my screen?
Yep, I see it. No problem.
Okay, so first I was thinking of doing something finance related, but I was having a lot of issues with finding kind of data, and I got kind of confused with what different like features and attributes that I might want. So I instead looked at Kaggle and then found an interesting data set. So the data set that I'm aiming to do some sort of cluster analysis of customer segment based on their behaviors, personality. So it contains like 2,240 people or items, and for each people they have like the date of birth, education level, mental status, income, and things like that. It outlines the different kind of products that they spend on, so wines, fruits, meat, fish, sweet, and gold. It also outlines the promotions that they have and the channels that they use. So in terms of the goals, I was thinking of like some sort of cluster analysis to identify the different segments. So group of like, what are the high income and high spending high income and low spending and vice versa, so that I can identify like maybe some of the key factors that would influence the high spending, high income, high income but low spending, and why is this? So this links to some sort of marketing plan that can actually be implemented. Yeah, but as for the details, because I actually just changed, so I'm not sure yet like which different attributes I might link. Yeah, specifically.
Do you have a question for me, or this is part of the study that you want to explore?
Yeah, I think that I can look, because right now I'm looking through a different resource that it's basically the same cluster analysis, but they're doing it through Python. But I can reference. But my question to you maybe is, right now, right, this is the current data that I have. It contains all these information, but like to form kind of specific connections. So for example, I say like, oh, there's a tendency that if you have more children, there's gonna be lower amount of like spending, and that can be a hypothesis. But then, can I incorporate external data sets, even though
yes, of course. But the point is, though, if you want to, okay, there are different ways of incorporating another data set. Okay, and this is a big thing. Maybe I have to spend quite a bit of time, but roughly speaking, if you have this data set, okay, the set of variables for maybe whatever 2000, okay, if you want to augment this with another set, it's going to be hard, because you're going to have to make sure that you actually have the same attribute measurement as the 2000, right? So what do you mean by if you have 2000 people on 20 attributes, if you're going to add another 1000, you have to make sure that you collect the same attributes, okay? And statistically, the other thing that you have to work with, and that's the problem, is you have to make sure it's from the same population. Now, chances are the Kaggle data guys did not generate or did not collect data from, say, customer in Thailand, right? So for you to augment it with another data set, it's not going to be homogeneous. It's not going to be 2000 plus another 1000. It's going to be 2000 plus another 1000 who are specially identified as Thai consumer or something like that. Okay, so it's a bit hard. It's a bit hard, and so you basically have to work with. I recommend that for now it's going to be too difficult to think about data augmentation. Data augmentation is important in professional data scientists job description, I guess. But I would not recommend you try data augmentation at this point. Okay, try to work with what you got. Now, you don't want to replicate, obviously, the study that's done. So you might do something else. You might say, okay, we can do prediction, or we can also do some kind of basket analysis. You know, you can do a lot of things without, you know, going over the same ground in the data. I really, I think it would be a little bit too difficult to for class project anyway to think about data augmentation. There is another thing called data augmentation algorithm that uses current data and then maybe adds a little bit of noise. Okay, that too is a little bit involved, and I don't really buy that approach all that much. So try to, unless you really you know, have your heart set on data augmentation, I would think that's a little bit too much, if I may say so. Okay, but it's very good that you're thinking about it. Okay, it's very good to think about it. The idea that you have one data set and you're going to apply to everything that's, you know, in machine learning, a lot of time what happens is this: you have like a huge data set that you can never possibly add to. But the model that's trained on that is applied on a different population. You want to apply similar kind of algorithm pre-trained, but to a different, slightly different class of population. This is called, in this case, this is called using the pre-trained model. Okay, and this is very valid. And if we have time, we'll go over that. Okay, so you use kind of pre-trained model, and then if you think about it, a pre-trained model can have like 20 layers of neural network. You chop off maybe the last 5 layers and retrain it, or something like that, make a new data set. Okay, that's doable. Okay. Okay.
So basically,
But,
your recommendation is maybe look more into like, you know, other maybe existing models and things like that.
I think you can deepen your analysis, different
Okay.
angles, different hypotheses, but still stick to the same Keiko data set because it's already clean and done for you.
So I can reference like studies and things like that.
Yeah, you can look.
Okay.
You can look at things like you know, cluster analysis from different algorithm, or using dimensionality reduction. Again, we talk about TSNE. We talk about, you know, you can do a lot of things with just one data set. So don't try to proliferate your database.
Okay.
Okay. Very good, Jin. Okay, excellent job. This is very good. Okay. Pim Nipa. Where are you, Kat? Okay, I see you. Okay. Okay, ครับ
หนูส่งลงไปในไลน์กรุ๊ปนะคะแล้วก็ Can you see my screen?
Prediction heart failure. Oh, that's very good.
So my project.
Also Keiko. Okay. Excellent. Excellent. Data source, observation, attributes, columns. Data set does not have any null value. Okay. Good. Good. And we are talking prediction.
Yeah, I'll making a prediction.
Good.
Yeah, and here's my data. I have already sent it to you. The data contains the data of 918 observation with 12 attributes, recently 918 patient with 12 health attribute as here. So what I've done is like I'm importing the data and then I'll just make it table form. Visualizing rows and column. Then I've created a separated file for firstly it's a hard CVS file. Then I separated from female and male, so I can like later on working with the visualization of gender comparison. Then
very good.
Then I set each data in each different category. I've already found the max, min, and yeah, anything. And here's my visualization. I've done a histogram visualization of each category compared by gender, like male and female. And here is a normal distribution of histogram. Yeah, and also a pie chart as well. So yeah. So what I'm looking to accomplish is like, I really want to know like how many percentage of male are commonly affected by heart disease compared to female, and yeah, which cholesterol value is good for heart and which value can cause heart disease. And here's already plotted on the list plot, but yeah, there's a lot of work to do because my data is way too big.
Okay.
That
okay? You've got a good head start. Like with Gene, I think you've done quite a bit already, so that's good. That's good. You have to be careful about scaling your data a little bit. I'm gonna send you a blog about scaling data. Now it's written about using sort of like a scikit-learn library, but the principle applies. So let me send that to you to make sure, because. And this is not just for you, but everybody who does machine learning. I haven't talked that much about pre-processing with scaling and all that. But let me send you before I forget. Okay. Okay. Copy. Let me send you this big. Okay, I'm gonna say for everyone, for every, Okay, check this one. This is good. This is very good. Well written as well. Some of the data science blogs are not good. Okay. Okay,ครับ. Very good. So Tim Nipa and Jean. Okay. Kanapum already went, right? So we go back to Kanakon, yeah?
สวัสดีครับอาจารย์
สวัสดีครับ. Okay, you have the floor. Go ahead.
Okay, so sorry, I'm outside and I don't have my computer with me right now, but I will try to share my screen. You see my screen, right?
ครับ. Very good.
เห็นใน screen ใช่ไหมครับ
เห็นครับ.
ใช่ครับคือ okay, so my data is also about the heart disease. I don't have the document with me at the moment because I'm outside, but so what I will do is I will try to make a prediction analysis about how to predict the heart disease possibilities in the future, and based on the information like blood pressure and maximum heart rate or
Okay. Good.
and to predict like the future.
This is not the same data set as Tim Nipa, right?
No, it's not the same one. My is the heart disease UCI. So I think it's lookalike, but it's not the same.
Yeah, so you should check each other's data set too. Maybe they'll give insight to each other's. Okay, but basically, yeah, these are basic medical diagnostics data.
Okay.
Again, medical data. You guys remember? Well, like when I take a blood test, right? Each blood test has a different range of values. Like cholesterol would be something like over 200 would be bad, whereas sugar over 100 would be bad, or something like that. So the scaling is quite important. Okay, so even though you have to work with the data that has a real unit, real life unit, and when you analyze the result, you have to work with real unit. Sometimes it's good to do some kind of data preparation scaling. Okay, so the same comment as I mentioned to Pim Nipa applies to you as well. Okay, so we go to Nat Phuket, right? Nat Phuket.
เรียบร้อยใช่ไหมครับ Thank you ครับอาจารย์
Okay, ครับ.
So I share my screen.
Yeah, go ahead.
Just show the data. Also, I will send you like the link to line.
Okay,ครับ.
So I'm doing like the breast cancer prediction. So based on the such as like the radius, texture, or some area, because I found like that like there are like specific area that the breast cancer is most likely to occur in a woman, and also like the tissue, like most of female have the tissue, which also like increase the risk of the cancer. And
Okay, that's interesting. Okay, very good. Male, female, diagnostics. Okay. Now, when you use Mathematica, obviously it's you don't have to think very much, right? You can say, please do me a prediction model, and it's going to give you what it thinks is the best. But for the project, I would prefer that you actually specify individual method and see how they come up against each other. Okay. So, okay,ครับ. Again, the data, if the data is not that big, Mathematica will just try all of them or something, okay, and give you what it thinks is best. But it's good to play around with different techniques. Okay, good. And this is going to be, what's the original source again?
Oh, I sent to you. Here. Here, I sent to you from via line.
Not yet. Did you send to me or to the group? Don't send to me because I don't think mine is public. Just send to the group.
โอเคครับ Here ครับ
Keiko breast cancer. Okay. Very good. Okay. Run training force. Okay, good. So you might even want to read the decision tree paper that I wrote earlier. That's also breast cancer, I think. Both diagnostic and prognosis. Diagnosis is whether or not you have the disease. Prognosis is now that you have the disease, what are your chances of surviving or something like that? Okay. Okay. Good. So it seems like a lot of you have are relying on Keiko, which is really is a good place. It is a good place to rely on. Okay. A lot of training example, a lot of and again, it does all this pre assessment, you know, the histogram and all that for you, so you don't have to do that. So good. So okay, Cap. So next week we'll I guess go more into nitty-gritty. I think I might spend a more portion of the of next week to discussing individual projects. So maybe instead of just 10, I might do the other 30 people. Okay, Cap. So very good. No homework for this week. Again, just review. You have my PCA notebook already, so I'm just going to send you bits and pieces and side note for today. Okay, Cap. Okay. Okay, Nat, Cap.
Yes.
Okay, Cap. Okay, Nat. I think that's good for today.
Okay.
โอเคครับน้องทำมาใช้ได้ทีเดียวแหละนะบางคนไปได้ไกลพอสมควรบางคนยังพอเริ่มแต่ก็ยังทิศทางดี so the only one I'm really worried is the dog color. Okay, you have to think a little bit. Okay ครับ but feel free to post what you found from the set that I sent you, the dog emotion. Okay. With that, okay, so I think we're good to go. I'll see you next week. Again, keep working on your project. Okay, now we're in the latter third, so you really should focus on the project now. Okay, cut. Okay, Nana, yeah, stop record ยังไง